Greetings, let's see what happens when we want to take a limit that looks like this. I mean approaching infinity of, let's say, this whole thing, x minus 2 minus x plus 2 in square roots like this. So if we have this, well, that's quite hard to tackle, but we can do something about it. We can use some algebra rules. So I can rewrite the limit and multiply it by the conjugate of this expression. That means the same thing, but instead of a minus here, we'll give it a plus here. And so we will get a fraction. I will multiply it by this same thing, but put a plus here, and multiply it both in the numerator and denominator. So it doesn't change the expression. It's like multiplying it by 1. So when we multiply it by the same expression by a plus here, we will make it a fraction and then divide it by that same thing again. We will make it expressed as a fraction now. This thing, the square roots will disappear, which is going to help. And on the bottom, we simply have the thing that we multiply the numerator and denominator by. So this thing with a plus in the middle. So the same thing, but with that plus in the middle, as was stated. And now let's see what we can do with this. There are some more rules. First of all, in algebra and also with limits in general, there is a thing that if you have 1 over x as a limit, as that x goes to infinity, it will go to 0. So we will use that as a fact, as like a pre-proven limit in a second. But first, let's manipulate the expression. Why we did this is we got an expression where, first of all, in the numerator itself, the x's cancel out. So we only are left with minus 4 in the numerator. But also, in the denominator, we have these roots, but they are added, which is less of a problem, because now I can isolate out a square root of x, and let's see what happens then. So I get a square root of x out of the equation, and what we get is 1 minus 2 over x in the first one, and then plus, and I can also isolate square root of x from the second one, and a similar thing will happen algebraically, which will be 1 plus 2 over x. All right, why this happened is if you isolate out something with the same degree square, basically it's like taking a fraction, taking a parentheses, isolating something out of a parentheses expression. It works the same way. So if you had a second root here, you can rewrite it as a product of two roots, where it's like a product of when you isolate out a common multiple. So that x times 1 can be multiplied back to give the x. The same goes to for 2 over x and 2. But this will be useful because what we have is honestly quite useful. We can realize that if 1 over x goes to 0, then 2 over x goes as well, because it's a constant very similar in size to 1. It's only 2 times bigger, but if 1 went to 0 and 2 multiplies it as a constant, that means that constant will go outside of the limit, and according to some other properties of limits, simply this expression goes to 0, and this one as well is the same one. Add it or subtract it. Then we're left with a 1 here. We are left with a 1 here. So in total, we are left with 2 square roots of x in the denominator. This is still limit, of course. So we would have limit of minus 4 over limit of square root of x times 2, which is minus 4 over 2 times 1 over square root of x. This thing is minus 1/2, so it's a constant. I can take it out of the limit. I can put the limit sign here. So whatever the limit will be, we are taking only of this argument, and this thing is a constant multiple outside. And now let's tackle this. We can also write it as minus 1/2, of course, and then limit, and the argument can be 1 over x, and all of that in a square root, because 1 is same under square root or not. It's the same expression. But 1 over x, as x goes to infinity, is 0, and square root of 0 is 0. So the whole thing is 0. So although it seemed evident from the beginning, we can make some steps to properly prove it. And there could be instances of limits that look similar like this one, and it's not evident as much. And so then this slow proof or many steps are even more useful.